Hello, and welcome to my physical science online course videos. In today's video, I'm actually kind of fielding a set of questions that came into my email about the second lab in the physical science class, which is Accelerated Motion Lab. So this is actually a series of questions that I'm sort of combining into one long video. Basically, there's been some confusion about this lab and how to go about doing some of the calculations involved in this lab. So I've put up on the screen the lab instructions that go with this lab. Basically, this is an accelerated motion lab in which you are rolling a ball down a ramp and measuring the position versus time as it rolls down this ramp. So you can see sort of the equipment and summary of experiment and so on. In any case, in the original instructions, there's sort of a sample of what your data should end up looking like. Basically, you've marked off positions in quarter meter increments. You're using a hand timer stopwatch to get the time at which the ball hits each of these increments, and then you repeat this 5 times and find an average for each position. So this is your average time at which you crossed that position in seconds. So this data should ultimately end up being graphed, and I actually have gone ahead and done that. So here are those positions, here's the times, here's the average time. I've highlighted in green because these are the things that are actually going onto the graph that is made, and here is a version of that graph. So here are basically what those data points look like. I went ahead and fit a curve to this data. A question that you're supposed to be answering in the lab is, what kind of graph is this actually making? And the way that you go about doing that is that you look at this graph and you can see it looks kind of like it might be a parabola, perhaps. And so the procedure is that you should square each of these axes in turn and then make a new graph. And so this set of data involved keeping the time axes as is. So I've taken these average times and copied them down here, and that's my time axes. Here are those same positions here. This is what the time axis squared values would be. This is what the position values squared would be. And the thing that you're supposed to be doing here, this graph is showing what happens when you square the position but leave time alone. And so you see you still end up with a curve. This is basically the best fit line that would be generated for that, and it clearly doesn't fit this data at all. So this was squaring the position axes and leaving the time axes alone. I have also made a graph in which I left the position axes alone and squared the time axes. And here is what that graph looks like. Again, this is using just example data for a 10-degree angle of inclination. And in this case, the data lines up pretty well with the line. So the answer is this a line? Yes. And therefore, since I squared the time axes and left the position axes alone, when we come up here and look at this graph here, that implies that this is in fact a parabola, and specifically it's a parabola of the type y equals x squared, or position equals something times time squared. So that's a walkthrough of what a lot of the graphing part is. From there, you should be finding the slope of this line and using that to determine acceleration. So I'm going to go ahead and move that out of the way, scroll down on this directions. Now that was for this 10-degree example. You are supposed to be doing this at a set of other angles, maybe 1, 2, and 4 degrees. And so you're trying to figure out what kind of graphs you get uh, without adjusting any axes. So if your graph looks like this, I guess you could say it's a curve. You might even guess it's a parabola, although you may not know whether it's a parabola or some other curve until you've gone through this process. So go ahead and answer that with curve tentatively. And then this process right here is for basically taking your data and squaring your axes to make these graphs. And once you've made these graphs, one of them may be a line, and that tells you whether this was a parabola or not, and whether it's a vertical parabola or a horizontal parabola or what have you. So then this part right here, the slope of your line is 1/2 the ball's acceleration in each case. So let's look at these sample graphs again. So this one right here, yeah, I have a line of best fit, but it fits terribly. So we basically discard this information at this point. We don't need it anymore for the lab. All it does is tells us that that was the wrong axis to square. This right here is what is more important to us right now, because now we have a line of best fit. So now we need to figure out what the slope of this line is. And so let me go ahead and zoom in a little bit on this graph, because what I'm going to need to do here is figure out the slope of this line. And the way that I'm going to do that is I've got to pick 2 points that are on this line of best fit. So let's go ahead and pull up a little workspace to use for me here. So let's sorry, I don't want this thing. So let's find a couple points on this line at best fit. So I basically need to find a point that I can define on this line. It looks to me like I am going through maybe this point right here, which is looks like maybe 1.2 comma, or excuse me, 1.5 comma 1.2. So let's just call that 1.50, and remember that this axis is in seconds squared, comma 1.2 meters. And so that's one point that's on this line of best fit. Now I need to know another point that's on this line of best fit. So ideally I would get 2 points that are reasonably far apart. That's kind of hard to do with the particular graph that I have here. The grid is not very fine, and unfortunately I can't work very well on this software with a finer grid yet. But let's take this point right here, which seems to be about 0.5 comma maybe 0.4. So 0.50 seconds squared comma 0.4 meters. Okay, so if I want to find the slope is given by rise over run. And rise over run symbolically looks like slope equals delta y over delta x. So whatever's on the y-axis, position, and whatever's on the x-axis, time squared. So the delta y part is going to be 1.2 meters minus 0.4 meters. I'm going to divide that by the delta x, which is really a time squared. So that's 1.50 seconds squared minus 0.50 seconds squared. Okay. So at this point, it would be useful to pull out my calculator to finish this calculation. So 1.2 minus 0.4 is going to give me 0.8. So I have m is equal to 0.8 meters divided by this time, which is 1.5 minus 0.5 should give me 1. And so it's going to be 0.8 over 1.00 seconds squared. And so that is 0.8 meters per second squared. So now I have the actual slope for my line of best fit. The next stage after that is basically to get a acceleration from this. And what you can do for that is that the instructions tell you explicitly in this lab manual the slope of your line should be half the ball's acceleration in each case. Okay, so my slope is 0.8 and the equation is m equals 1/2 a, where a is the acceleration and m is the slope. And so what that implies is that the acceleration should be twice the slope, which is twice times 0.8 meters per second squared. And so that is 1.6 meters per second squared. By the way, I'm not being particularly much of a stickler here with significant figures. If I was, then this right here would need to be rounded off to one significant figure. Using this graph, that's probably about as good as you're going to get. But you can make a more thorough graph than the one that I've made because you're not having to try and demo this on a screen. So hopefully you can get at least two significant figures. So what should the acceleration actually be here? Because the last step is to try and get an experimental minus a theoretical. And notice that it says here the theoretical acceleration should be 9.8 meters per second squared times sine of theta, where theta is the ramp's angle of inclination. Okay, so at this point we should pull up our calculator again and take 9.8 and multiply it by that angle of inclination, the sine of the angle of inclination. So the angle of inclination was 10, so the way we enter it is 10, push sine, hit enter, and so I get that the slope should be 1.70. So this right here is experimental. So theory, whoops, that should be a colon. My theory says that the acceleration should be 9.8 meters per second squared times sine of 10 degrees, which was approximately 1.7 meters per second squared. Okay. So here I've got a theory and I've got an experimental value. So now I need to figure out my percent error. So let's pull up again the lab instructions to see what that means. So your experimental error is basically this guy. So we need to have experimental value minus theoretical value over experimental value times 100%. So that looks like this. 1.6 meters per second squared minus 1.7 meters per second squared divided by 1.6 meters per second squared. This is our percent error. So this guy is times 100% to make it into a percentage. And so this part up here gives us 0.1 over 1.6. Notice that the units are all the same, so we can kind of cancel out the units because it's common to all three factors. It's 0.1 over 1.6 times 100%. So pull off our calculator once again, and 0.1 divided by 1.6 gives me 0.0625. That times 100% says 6.25%. So we can say that the percent error is about 6%. There's one last thing that we're supposed to do in this lab, which is that we have this comparison of average speed versus the theoretical time that it should take, the theoretical average speed. And to do that, you can start off with the data that you collected earlier in the experiment. This is to get the experimental value. In this case, the ramp is 2 meters long and the average time was 1.57 seconds. So the experimental value of the speed can be obtained as follows. So we have a time value of t equals 1.57 seconds to travel a total distance delta x of 2.00 meters. So the average speed is defined as the distance divided by the amount of time that it took to go that distance. So that's 2.00 meters divided by 1.57 seconds. So out comes our calculator again. It's 2 divided by 1.57. And so our speed average is 1.27 meters per second. So we write is approximately 1.27 meters per second. And then for the other part, we need to look down here. There's a theoretical value for the time, which you can therefore get the average speed using the ball's acceleration. So the time should have been square root 2 times distance over acceleration. So the value for the acceleration is 1.6 meters per second squared. That means that the theoretical value for the time should be square root of 2 times 2.00 meters divided by 1.6 meters per second squared. So let's go ahead and stick that stuff into our calculator. So 2 times 2 is 4 divided by 1.6 gives us 2.5, and now we take the square root of that and we get 1.58. So the theoretical time should be 1.58 seconds. Okay, so now coming back on here, what we're looking for is actually the theoretical average speeds. So we have the time. This is the theoretical time. And we have the distance. So the theoretical speed average should be 2.00 meters divided by 1.58 seconds. So that's going to give us 2 divided by 1.58, 1.27. And within the level of certainty imposed by our significant figures, there's no real difference between the theoretical, and this up here of course was the experimental value. So we could even put like an EXP for experimental. The two are the same, so that's a 0% error in this case. So that is a more thorough walkthrough of this lab than in my other video as far as actually seeing what the calculations involved are. I hope that you guys find this supplement helpful, and good luck with the lab.